When you're studying chemistry, you're looking to explain the material world around you, that's the stuff, what it's like, and you do that in terms of the atoms, the microscopic things you can't see and how they might be interacting with each other. In senior chemistry, that's a lot about how electrons move between different atoms. So we start at senior level chemistry with understanding that core atomic structure. And then we use that to explain the different types of bonding that occur, the general substance types that we have. The later units will then start to focus on some of the more important substances. Water is absolutely vital to our world, and particularly how water can dissolve different things. Another crucial aspect of chemistry is the chemistry of carbon. We call that organic chemistry. The versatility of carbon means that there are so many different things, compounds that it can make. In year 12, we tend to extend that understanding and look at the different types of reaction mechanisms that can happen with some more extensive reactions. People often ask, how much maths do you use in chemistry? I think it's important to recognise that the conceptual understanding of the models is so important. Then the maths you have to do to describe that is fairly straightforward. It's multiplication and division. Yet understanding the ideas behind that will mean that you put the numbers into your fairly straightforward equations. So maths is vital for explaining, but the level of mathematics is not particularly demanding at senior chemistry. Practical and theoretical work in chemistry are inextricably linked. You can't really do one without the other. The practical work that we use might be the hook to get you into a particular topic area, or it could actually be the end point where it's really probing that deep understanding. And then in other occasions, it's actually an integral part of the process of learning. So the two things always go hand in hand. We're always thinking about one and potentially doing the other. So if we want to use some chemistry, some ideas and models to illustrate how that can impact our macroscopic world, things in the real world, a really good example might be to heat a substance like sulfur, which we see as a yellow powder that's fairly soft. When we heat it up, we can actually get those molecules to change their structure such that we can make them form crystals, or we can turn them into rubbery substances. So under control, the students would perform a set of specified tests, and those tests will examine some of the straightforward properties and how they change. There are some instances where if we want to show something that requires probably more extreme heat and maybe has some issues in terms of the fumes that produced, then we might have to do that as teacher demonstration where the students will observe those properties occurring. Wherever possible, we want them to experience the learning themselves and see the practical. All the chemistry they do is relevant to the world of the student. If it isn't real and not relevant, then the question is, why would we be doing it? Beyond senior chemistry, there's then multiple avenues that our students go into. If students then go for further study, only a small number of chemistry students will actually study chemistry at tertiary level. But chemistry will be a foundational subject in so many of the different careers that they have, the medical careers that we traditionally think about, but then they could also be in pharma. It could also be in energy sector, where it might have been petrochemical in the olden days. Now there would be the fuel cells, the emerging technologies that require a chemistry understanding. So there is so many fields which students will go into where chemistry will be a core component of their foundational training.